Okay, today's lesson is on logistic growth. So let's talk about how this is different than some of the other differential equations we've been looking at. All right. So on logistic growth, what we've been dealing with is exponential growth. These are the types that we've been dealing with. And if you look at the differential equation associated with them, we are assuming the rate of increase or decrease is directly proportional to the population. So this is the kind of differential equation we've been looking at. This one right here. This would be an exponential version. These we have learned how to work with them fairly extensively. We know how to go backwards and get the position or the original equation from them, and some other things. So we have worked with these quite a bit. This is a new kind. It's called logistic growth, and what it does is it basically, in some real life situations, we're not going to be able to grow exponentially forever to infinity. There could be some limiting, it's called a limiting capacity or carrying capacity. The growth levels might, as they approach a limiting number, which is called the carrying capacity, they might, taper off. So maybe limited resources. You can't have an infinite number of fish in the lake. There's not enough to support them, or whatever scenario they will come up with, wolves or bears or anything like that. You can't have an infinite number of them because there's not enough resources for that. So that's a logistic growth problem. In this type, the rate of increase or decrease is directly proportional, but it's to both P and L minus P. So this is the type of differential equation we will be working with. That is the standard form for logistic growth. Now, on these type, the lesson today, we are not going to have to go backwards and get the position. We're going to be able to find everything that we need from just the derivative. And so that's, I guess, one of the benefits. And actually on the AP test, they will not expect you to be able, or they're not going to test you on being able to go backwards from this and find the population equation. Now, we are going to do that tomorrow. We are going to do a lesson on that. But that actual part of it, the finding the position function, is not tested on the AP test. But you will be expected to take the differential equation for logistic growth and be able to answer all these types of questions for it. And that's what we're going to work on today. So, first of all, one more thing. Notice that the second derivative does give us information that's important in the equation. And we certainly can find the second derivative. That's not an issue. Finding the second derivative from there would be pretty straightforward, and we will practice that. Okay. All right, this standard form of the logistic growth differential equation is actually pretty important. As with many formulas, like a formula of a circle or ellipse, if you get it in standard form, you can read things out of it, like the center and all that kind of stuff. Well, if you can get your differential equation in this standard form, you're going to be able to read the limiting, this L, the carrying capacity is what they call it, a limiting number L, the carrying capacity. So for part A, previously, we have had to go and find the position function and do the limit of it to infinity. In this case, if we can simply put our differential equation in this standard form, we're going to be able to read the answer off of it. We're going to be able to read the carrying capacity out of the formula. So that's one reason that we don't have to go backwards to get back to the position function. So that's the first thing that I'd like to do, is I'd like to take this differential equation and write it in that standard form. Notice how it's a factored form. So we need to factor a P out. Let me clear it up so you can see it a little bit better. And the P has to have no number in front of it. It needs to be a constant of 1. So let's get this differential equation written that way. Alright, so we would have dp dt equals 1 over 6,000 p times 18,000 minus p. Okay, this number is our L, or our carrying capacity. So when they ask us what the limit of the original function is to infinity, well, it's going to be 18,000. We don't even have to find the original function to know that. We just write our differential equation in standard form and it gives us the information. What is the range of the solution curve? This is pretty straightforward. Basically, it's going to start at the initial population and it's going to go to whatever your limiting number is. That's your range. You can write it in interval notation or set notation, doesn't really matter. So we'll say we're going from 4,000 to 18,000. We could put brackets here on the 4,000 because we actually do equal 4,000. And we probably won't equal 18,000. I mean, it's possible, but we're not going to consider that we would. Okay, so that's the range. Now, to find out whether we're increasing or decreasing, whether p is our original function, we've been doing that kind of stuff for months, right? We know we take the derivative, we set it equal to 0, we do a sign chart. We already have the derivative right here. If I set the derivative equal to 0, I think we can see that I would get 0 for p, but that's not possible, right? Because I'm starting at 4,000, I'm not starting at 0. So I really need to start my sign chart out at 4,000. And we've just discovered that we can't get bigger than 18,000. That's our limiting number, so we go to 18,000. And then I simply test the signs in my first derivative, and I get, for this one, we get that it's positive. So that means we're increasing from 4,000 to 18,000. And they want us to justify, so we would say, like we always do, because the first derivative, which is dp dt, is greater than 0. And we're not decreasing at all. You can say that we're not decreasing. We're not decreasing, and if that, we could say because the derivative is not negative. Okay, and that deals with increase, decrease. Okay, we okay with that? Now, let's talk about concavity. And just like we always have, concavity comes from the second derivative. So we're going to have to find the derivative of this differential equation that we're given. Now, I would prefer to find the derivative from this form rather than the factored form. Otherwise, I would have to do like the product rule, and I would really prefer to avoid that. I would just go back to the original derivative, the way it looks, and find the derivative there. So let's do that. Let's find second derivative. So d2p over dt2. So second derivative equals 3. Remember, we have to tag it since we're in the second derivative. We're going to have to say dp dt. And then minus p squared over 6,000. I'd do my power rule. I'd get 3,000. So p over 3,000 dp dt. Okay, if we factor out that dp dt, we get our second derivative is equal to dp dt equals 3 times, let me fix that. Okay, so it's the first derivative times 3 minus p over 3,000. Now, this first derivative, this representation of the first derivative, you could, if you wanted to, take, the first derivative and put it in there, but we already know the sign of the first derivative in this interval. It's positive. We have to consider that, though. We can't just ignore the first derivative part here of the second derivative. We have to take it into consideration when we do our sign chart. So we need to do a sign chart for our concavity. Alright, so we would start at 4,000. And then our this piece right here, our second derivative, we would set that equal to 0. And P would become 9,000. So that goes on our sign chart. And then our limiting number is 18,000. And then we do sign analysis on this. Please keep in mind, now on this problem, our derivative, first derivative is positive, so it's really a non-issue when we're doing the sign chart. But on one of the following ones, it's going to be negative. So just pay attention and just be sure you know what the sign of the first derivative is. So between 4,000 and 9,000, we know our first derivative is positive, and if I put a number between 4,000 and 9,000 in my second derivative, I will get a positive number. Then if we go between 9,000 and 18,000, and I put, say, 10,000 in my second derivative, I know my first derivative is positive. That's positive. And I put 10,000, I'm going to get negative. And so those are the signs of my second derivative. And we are concave up from 4,000 to 9,000. Because the second derivative is bigger than 0. Just our normal reason. It is asking for justification. And we are concave down from 9,000 to 18,000 because our second derivative is negative, less than 0. And that's our concavity. Okay, see, a lot of this is review, right? The only crazy thing about it is the whole logistic equation and how to read it. To remember the standard form. If we don't remember the standard form, we're going to be at a loss. And we're going to have to find the position function, which actually takes a little while. We're going to be doing that tomorrow. So we really do want to remember the standard form of the logistic growth equation so we can read our limiting number out of it. Okay? All right, inflection point. Does this have an inflection point? Yeah, we have a change in concavity, right? So, yes, we have an inflection point. Our inflection point is when P, that's the position that we really don't know. We don't know what the equation looks like, but when that position function is 9,000, that's the y value. It's kind of strange, I know. When that position is 9,000, then well, we have an inflection point when it's that, because my second derivative changes sign. It changes, you can just write changes signs, or you can say changes from positive to negative. So we do have an inflection point. Okay, now let's look at a logistic graph. This is a normal standard problem. This is what a normal logistic graph looks like. We're going to have a limiting number. That's our 18,000. It's going to look like a horizontal asymptote. We have 18,000 here. We're going to start the graph. This one starts at 4,000, so, somewhere above like that. Our inflection point is at 9,000, so that's also an important number. And we are concave up, so we're going to go concave up, and then we go concave down right here at 9,000. So our concavity changes at 9,000. Now, if you remember back up here, when we find the second derivative, we can find out an important fact about the time when it's growing the fastest. Well, it's growing the fastest at its inflection point. And that's something else you would have to remember. That's a normal question that they would ask you. When is it growing the fastest? When is the population growing the fastest? And you would have to find the point of inflection. That's when it's growing the fastest. And in this case, it would be growing the fastest at 9,000, when P equals 9,000. Okay, so that's another typical question that you would get. So this is a normal logistic growth graph. If you remember exponential graphs, the kinds that we were dealing with, they would look like that, just increase forever, right? Or the reverse, decrease forever, well, to 0. So those would be exponential graphs. This is a typical logistic growth graph. Okay, see the difference between the two? Now the other two problems that I have on the second slide is using all of the same information that this does, except it has a different initial condition. So we have the same derivative, we have the same second derivative, so we don't have to do any more. We have the same information to deal with. So the other two problems are going to be much quicker because we already know what the first derivative, second derivative, all that is. We already have sign charts for much of it. So let's go and let's look at the second two problems. And the reason that I'm showing you those is because they're unusual. This first one is typical. That is a typical logistic growth problem. The number 2 and 3 are unusual. And so we need to look at what that would look like. What would it look like if it were unusual? Get this out of the way. So let's look at the first one. Our limit, we have the same equation, all the same stuff going on. Our limit is going to be exactly the same. It's that 18,000 that we found in the first one. Nothing has changed with that. Our range is going to change, right? Because we don't get to start at 4,000 anymore. We're starting at 10,000. So we go from 10,000 to 18,000. Okay, so our range did change. Our solution curve, increase, decrease. The only reason it's changing is because we are knocking off part of the sign chart, right? We don't get to go all the way down to 4,000 like we did with our other sign chart. We actually have to start this sign chart at 10,000. So we start the sign chart at 10,000 and we go to 18,000. And look, all that part is chopped off. The inflection point's gone. The concave up is gone. I mean, all that stuff is gone. What were we doing down there? I think we were always increasing. So we're still increasing for the increase, decrease. We're still always increasing. So we're going to increase from 10,000 to 18,000 because the first derivative is greater than 0, just the same as the others. We're not decreasing at all. You can write out the not decreasing part if you want. The concavity is going to be different though because we've chopped off the first part of the concavity sign chart. We just get to go from 10,000 to 18,000. And if you refer back to your original sign chart, you will discover that this section was negative. That was a negative section on our original sign chart. We don't get any concave up in this case. That's all been taken out. So this is simply concave down from 10,000 to 18,000. And it's because the second derivative is less than 0. Because the second derivative is less than 0. Okay, so do we have an inflection point in this situation? No, we don't, because we don't have any change of sign in the second derivative. No, because the second derivative does not change sign. In 10,000 to 18,000. Okay, so it doesn't change sign. So the graph is going to look different, right? The graph is going to look different. It's going to still have that limiting number at 18,000, but we don't get, an inflection point anymore. We're actually starting at 10,000. And we are only concave, concave down. So it's going to kind of go like that, right? There is no concave up part. So this is a logistic growth graph, but it is not the norm. Normally they have an inflection point, and this one doesn't. Does that make sense? So we needed to see one like this. Questions so far? Okay, the third type, also different. This one. So we're changing again. The only thing that's changed, all the equations are the same. The only thing that has changed for us is our initial condition. And our initial condition is at 20,000. Now that's kind of strange. We are actually starting over our limiting number. Our limiting number is still the same. It's still 18,000. Our range, of course, changes as our initial condition changes. Our range goes from 18,000 to 20,000, which is very strange. So our graph is going to start above the limiting number. A scenario that, so this is talking about, I think, fish. Is this the fish one? Yeah. So a case like this would be, let's say they put too many fish in the lake. They're too many for the resources to handle. That means that they would die off until they got to a level where the resources around them could handle them. That would be a situation like this. Now, it's also unusual. This is not a normal logistic growth curve that you would see, but we need to see it just so you can see all the different combos. All right, now we're going to have to, we didn't really pay attention to the sign charts over 18,000, did we? We're going to have to go back and redo our sign chart because we really don't have data over 18,000. All right, so for our increase decrease, we need to go back and mess with the first derivative. We will see that the first derivative from 18,000 to 20,000 is negative. Okay, that's negative. So that's going to be an issue when we get to the second derivative. Think about why. Why is that going to be an issue when we get to the second derivative? Because when we do a sign chart for the second derivative, the first derivative is no longer positive. You know how we were kind of ignoring it because it was positive? Now the first derivative is going to affect the sign of the second derivative when we do a sign chart for concavity. It's going to affect it. All right, so here, let's answer the question. We are decreasing from 18,000 to 20,000 because our first derivative is less than 0. It's our justification. So let's do our second derivative sign chart. And in going back and testing the signs in the second derivative, we're taking into account that the first derivative is negative. We go back and test the signs and we find that our sign for the second derivative in this interval is positive. So we are concave up from 18,000 to 20,000 because our second derivative is greater than 0. Okay, do we have an inflection point in this scenario? No, right? It was chopped off long ago, right? It was way down there at 9,000. That's gone. So no, and the reason would be the same as up here, that it doesn't change sign. So no, the second derivative does not change sign. Does not change sign on 18,000 to 20,000. So let's look and see what this graph would look like. I would still have my kind of like this horizontal asymptote here at 18,000. But now I'm starting above. Again, this is unusual. You don't normally see the curve start above the limiting number. But we're starting above at 20,000. And then what happens to it? We're supposed to be decreasing and we're supposed to be concave up. So it would look like that. Okay, and those are really the 3 different scenarios that you will encounter. And they love these kinds of problems. You will probably see one. Okay? Are we okay?